We did some really heavy-duty calculator work last day. I spent lots of time. We said we're going to use ditto marks. We said we're going to backspace. We said we're going to edit because otherwise the likelihood of making mistakes is really, really high. And we left off talking about escape velocity. I'm betting you've heard the term escape velocity. If you watch sci-fi movies, they talk about it. What is escape velocity? Well, in layman's terms, it's how fast you need to go so that once you reach that speed, you can cut off your engines and coast to the edge of the universe. You've escaped the gravity well of whatever planet you're in. In physics terms, it asks how much work is necessary to bring our potential energy to zero. We can solve for escape velocity using conservation of energy. We can solve for escape velocity by saying potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. Where final is the edge of the universe out to infinity. That's in our mathematical model, Simone. In reality, final is you've freed yourself from whatever planet you're trying to get out of, and now you move on to your next destination if we're in our Star Trek universe. What did we define the amount of potential energy to be out at infinity last day? Do you remember? Okay, we defined this to be zero. That was defined that way. We said out at the edge of the universe, since there's no gravity acting on you, there's nothing pulling on you, you won't fall. And since you won't fall, you don't have any potential energy. Second thing we're going to do is we're going to imagine, Michaela, we are so good with our numbers that when we fire our rocket and then we coast and we coast and we coast, right when we get to the edge of the universe, because we're slowing down the whole time, because gravity is acting on us the whole time, right when we get to the edge of the universe, we're slowing down, we're slowing down, we're slowing down, we're slowing down. And we're going to time it so perfectly that we come to a stop right at the edge of the universe. In other words, we're going to time it so perfectly that that's also true. Because we can mathematically, Sarah, so why not? Let's be good. We're going to say that our kinetic energy is going to be zero because we just came to a stop, James, right then at the edge of the universe. And we've defined potential energy at the edge of the universe to be zero. So that means we get this. The right-hand side of the equation is nothing. Zero. Oh, and kinetic energy is a half mv initial squared plus. Why can't I do this? This is wrong. Don't write this down. Why can't I use that one? Okay, we're going cosmic now, so we have to use our new version of potential energy, which was negative big G, big M, little m, over, not r squared, just r. Joss, I'm going to plus that to that side and get rid of the negative. That's okay? So I'm going to get this, a half mv initial squared equals positive big G, big M, little m over r. Oh, cool. I also noticed something else. Do you see it? I guess it doesn't matter how big my spaceship is. All that matters is how fast it's traveling. So the escape velocity for the Starship Enterprise would be the same as the escape velocity for the Death Star, would be the same as the escape velocity for, Pluto's probe. And by the way, we have achieved escape velocity. The Apollo astronauts achieved escape velocity from the Earth. Once they got partways to the moon, they were able to shut their engine. Well, they fired their engines near the Earth to get fast enough so that they coasted the rest of the way to the moon. And once they got part of the way to the moon's gravitational field was stronger than the Earth and started pulling them in towards the moon and speeding them up. We want to get the V by itself. How? Yeah. And we get, I always like this, a really clean, pretty equation. Here's the equation for escape velocity. Instead of VI, I'm now going to call it V escape. And you said we're going to go times the 2 over, and then square root. R is the radius of our original planet. Big M is the mass of our original planet. V is how fast you need to go to leave, to get away from, to escape the gravity well of your planet. Hey, what's escape velocity of Earth? Hey, what's escape velocity for the moon? Let's draw a little line down the middle. Here's A, here's B. So, escape velocity is 2 big G, big M over R. So for the Earth, it's going to be the square root of 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, over 6.38 times 10 to the 6th. Apparently I need more room. Oh, wait a minute. I know what I can cleverly do. Alrighty. Again, this is good calculator practice for all of you because, you know, plenty of room for error we found last day. No yawning. 2 times 6.67, scientific notation, negative 11 times mass of the Earth, divided by 6.38. Did I type that right? Looks good. Square root of that. I know escape velocity, it's almost 11,000. Is it not 1111 or something like that? Yeah. Yeah. It's a little over 11,000. 11,200 meters per second. Which we can do with our current technology. However, it would be kind of nice, Julie, if in your lifetime we had a permanent base on the moon, because escape velocity from the moon is not this much. Because remember, where does this energy come from? The fuel that you're carrying to get that fast. That's a lot of fuel. So, let's do escape velocity from the moon. That's going to be the square root of 6.67 times 10 to the negative 11. I have no idea what the radius of the moon, or sorry, mass of the moon. It's on your sheet. 7.35 times 10 to the, sorry? 22? Okay. And radius of the moon, because that's where we're leaving from, is? You know, with a bit of cleverness, I think I can backspace and edit and just change some things. So I got the 2 and the 6.67 times 10 to the negative 11. 7.35 times 10 to the 22. 1.74 times 10 to the 6 square root of that. You get 2,374? 2,370. A little easier. Now, right now, though, that wouldn't be easier because to get that escape velocity, we would first of all have to send stuff from Earth via escape velocity to get to the moon. So right now it's not economically viable, but if we had a permanent moon base that was able to generate resources from the moon and generate fuel from the moon, then that would be a much more economically viable way to send stuff out. May it happen in your lifetime. I like example 5, I like example 5, I like example 5. Example 5 is a nice question. An 1,800 kilogram satellite is placed in a stable orbit with a speed of 4,200 meters per second. A says, find the orbital radius. And then B says, find how much work is required. Okay. Drake, what does A want me to find? Did you say orbit? Gravity is what's pulling me in a circle. I know from prior experience that we're going to need lots of room, so I'm going to work sideways rather than down and just use as much paper as I can, save as much space as I can. I know that gravity is big G, big M, little m over r squared equals, well, it's going to be mass, don't write this next bit down, times circular acceleration. Which circular acceleration equation do I want to use? How do I know? Oh, they gave me a speed, so I'll use that. Okay. So, Drake, it's going to be v squared over r. Once again, the little mass cancels. Does an r cancel here? Yeah, 1 does, because that r would move to the top, and then it would cancel with that one. And in fact, oh, now I want to get an r by itself, though. We've seen the v squared equals big G, big M over r square root the v to get the v by itself. Now I want to get the r by itself. I think, Drake, I'm going to move the r up to here and the v squared down to there. I think I'm going to have this. R equals a big G, a big M over v squared. And this I'll call all r orb, just to distinguish it, because that's what you said we were finding, the orbital radius. It's going to be 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th divided by 4,200 squared. I'm getting a bad vibe from this question. Let's see. I'm doing some math in my head, and I hope I'm wrong. One, two, three, four, five, six. Oh, 7. I was doing some quick math in my head, and I didn't carry a 10 right. I was getting a radius underneath the Earth's surface, thinking that I'd made up really, really bad numbers. Whoops. But no, it's 10 to the 7th, not 10 to the 6th. I was getting 2 times 10 to the 6th. That's inside the Earth. We don't orbit there. Whew. So I'm going to, since I know I'm going to use this, trust me, I'm going to carry some extra sig figs. I'm going to go 2.2611 times 10 to the 7th. Meters. Hey Max, what does B want me to find? Ah! I seem to recall Mr. Dewick last day saying, boy, you know, finding that amount of work is an awful lot of work. And I mean that both as an answer, but as a procedure. Okay. Work equals, don't write this down, force times, why can't I just go force times distance? It'd be gravitational force, technically times radius. Why can't I do that? Because as I go further from the Earth, what happens to the gravitational force? Changing. This equation only works, no pun intended, for constant force. It would also be the area under a graph. Last day I showed you, though, that area was a curve. So, our more universal work equation, the work energy theorem, work is going to be the change in potential plus the change in kinetic. I said these are complicated enough that I even tend to break this up. I'm going to do change in kinetic separately from change in potential. I'll do change in kinetic first. Why? Because I think last time we did change in potential first, and it really doesn't matter. Nikki, what's change in anything? See how it's all coming together? And remember, Nikki, last day I said we're going to assume worst case scenario that our initial speed at rest. And I said that's technically not true. Where would that be true if we were launching from? North or South Pole. So we said we're going to be launching from Superman's Fortress of Solitude from the North Pole. For those of you that were away, because the Earth is rotating, you actually have some kinetic energy from the rotation of the Earth. So you three that were away, where would be the best place on Earth to launch rockets from? No, that's the worst place on Earth to launch rockets from. The equator. We don't have too many space nations along the equator, but it's why the U.S. launched from Florida as far south as they could get. It's why the Russians, one of the reasons the Russians had so much trouble with their space program is they didn't have access to anywhere further south. They had to build these massive rockets because they were getting almost all their kinetic energy from the rockets, where the U.S. could get a kinetic energy boost from Florida. But where would the best place to launch be? It's why Elon Musk is trying to build launch platforms on ships, because then you would just put the North Pole, that's where the Earth's rotation is essentially zero laterally. So we're launching from Superman's Fortress of Solitude. Which V? Orbital speed. So it's going to be 0.5. Oh, we got a latecomer. Mass of the probe was 1,800. And orbital speed 4,200 squared. 0.5 times 1,800 times 4,200 squared. And I get how much kinetic energy, and again, this kinetic energy is coming from fuel, so to get it in that orbit is going to take 1.58676 times 10 to the 10th. 1.5876 times 10 to the 10th joules of rocket fuel. That's how much fuel you need to keep this thing in orbit. How much fuel do you need to get this object to the correct radius? Well, that's going to be the change in potential energy. Brendan, what's change in anything? And none of these will be zero unless you happen to be at the very edge of the universe. Okay? There might be, I think in the big review, there's a question where you start at the edge of the universe a long distance away, and so your initial potential energy would be zero. Yay! And there's another question, I think, where you end up at the edge of the universe or a long distance away, and your final potential energy is zero. We're not doing that. We're going into orbit. So it's going to be negative big G, big M, little m, over our final minus negative big G, big M, little m, over our initial. Negative big G, hang on, Mr. Duke, you to plug in numbers. Negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. 1,800. My final radius is my orbital radius, which Drake, you and I calculated. This is why I wrote it down to extra sig figs. 2.2611 times 10 to the 7th. 2.2611 times 10 to the 7th. Brendan, what's a minus minus the same as? Okay. And then for the 3 humans that were away last day, actually 4 of you, Jen, here's what we decided, because this is so much. I went on a big rant last day about how, Robbie, by far the most common mistake is calculator errors. I've lost track of how many times I see kids have written everything down right, totally wrong answer. So you ready? We're going to take some intelligent shortcuts. Big G, ditto mark, times big M, ditto mark, times M, ditto mark. Do that. Write that. I'm serious. And make sure you watch the video lesson because I've explained why this is the case. Divided by, now our initial radius, we're taking off from the surface of the Earth, so it's going to be 6.38 times 10 to the 6th. Get out your calculators, everybody. Remember, we're not going to do this all in one fell swoop. Instead, we're going to type the first expression, negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 1800 divided by 2.2611, scientific notation button 7. I'm going to get an answer for the first term, the first fraction. I'm going to write that down to like 5 sig figs or so. Negative 3.17526. Negative 3.17526. Negative 3.1752526 times, what was it? 10 to the what? You get 10? And I told you, ballpark figure, typically in orbit around Earth, you'll be 10 to the 9th, 10 to the 10th, or if I put you way out there, maybe a 10 to the 11th, but that's got to be way out there. So typically it's going to be a 10 to the 10th. So we hope we did it right. Plus, and this Robbie, this Connor, this Brendan, this Jen is why I've yelled at you about getting a good calculator. You're going to backspace, delete the negative, fix the new radius, 6.38, scientific notation button, and delete what's there. It's less typing, and that means less chance for error. Did you get that first term? No. So you need to watch the video lesson. As I said, one of the biggest mistakes. Here's one of the biggest mistakes. I don't mean him. I mean making one of the. You know what I mean. Calculator errors. 1.12533. 1.12533, and here I get times 10 to the 11th. Is that right? Anybody else get the same thing? Okay. We're going to add these together. Thankfully, I have this number stored, so really I just got to add the negative 3.17526 times 10 to the 10th. And I get a change in potential energy of 8.0780 times 10 to the 10th. At the very beginning of this, we said that the amount of work is going to be the change in potential plus the change in kinetic. This second box is the change in potential. This first box is the change in kinetic. I guess I'm going to add them together. Final line. Work is going to be the change in potential, 8.0780 times 10 to the 10th, plus the change in kinetic, 1.587, write this down correctly, Mr. Duick, 1.5876 times 10 to the 10th. Thankfully, I got this first number still stored, so I just got to go plus 1.5876 times 10 to the 10th. How many joules of energy would this take? How much work would this take? And if you knew how many joules per liter of energy you got from your rocket fuel, you could easily calculate how many liters of rocket fuel will this take? 9.67 times 10 to the 10th. That's bare minimum. Who remembers what are we ignoring in this whole shebang? Air resistance, which at those speeds would play a huge part going through the atmosphere until you got to outer space. But again, it's why all rockets are designed aerodynamically. Whew. That's not the longest question yet. That's the second longest question. What's the longest question? Next lesson. I already said you could do 1, 2, 3, 4, skip 5, skip 6, 7. You can try number 8. Number 9. Now, if you're moving out to an infinite distance, and it doesn't mention any speeds. I think for number 9, you can assume your initial speed on the launch pad is 0, your final speed out at the edge of the universe is 0, and at an infinite distance, what's your final potential energy? 0. So this isn't as bad as you think. Lots of stuff will cancel for that work equation. 10 is good. 11 is good. Skip 12. 13 is good. 14. 15. Mr. Dueck? Yes, Drake. Please, Mr. Dueck, I've been dreaming all weekend. Please, will you teach me how to build a Death Star? Okay.